So far in our discussions of probability distributions, we've only dealt with a single random variable at a time. Now, oftentimes, we're going to have more than one random variable at a time. To deal with those, we're going to use what's called a joint probability distribution. And these can happen with either discrete random variables or continuous random variables. So we're going to take a look at both today. We're first going to take a look at joint probability distributions for discrete random variables. So we have two discrete random variables, x and y, and we know that a function f of xy is a joint probability distribution or probability mass function of those discrete random variables. So before, when we were talking about the probability mass function for a single discrete random variable, we had that our function had to be greater than or equal to 0 for all values that that random variable could take. Now we're going to be doing the same thing, except for this time our joint probability distribution can have a value for the discrete random variable x and one for the discrete random variable y. So we need that our function is greater than or equal to 0 for all possible ordered pairs this time. When we were talking about the probability distribution for a single discrete random variable, we needed that the sum over all of the values that that random variable could take of the function would equal 1. Well, now the function is going to be taking a value from each of x and y, two discrete random variables. So we need the sum over all of the x and the sum over all of the y. So we're going to put basically all of the possible ordered pairs in here, and we're going to add up all the values that our function takes, and they need to be 1. And again, when we were looking at the probability distribution for a single discrete random variable x, the probability that that random variable x took on a value, lowercase x, was equal to the value of the function at that lowercase x point. Now, since we have both a value that our discrete random variable x and a value that our discrete random variable y are taking on, the probability that it takes on that pair of values is going to be the function evaluated at that pair of values. Finally, when we were talking about the probability distribution for a single discrete random variable, we were talking about an interval instead of a region. So now that we have two, these things are going to turn into regions. So before we had an interval, and now we have both those x values and we have y values, and they can take on anything in that area, making us have a region A that we're talking about. All right, so if I want to know the probability that my discrete random variables x and y take on a value somewhere in this region, I'm going to actually sum over all of the xy coordinates in that region the value of the function at those coordinates, and I'm going to find that total probability. Additionally, there are times when we don't care about the entire joint probability distribution, and instead we're more worried about what's called a marginal distribution. Marginal distributions take one of our random variables alone and tell us about probabilities associated with it. So, if I want to know the marginal distribution of x alone, what I'm going to do is take the sum over all the possible y values given that fixed x value of my joint probability distribution, f of xy. And similarly, if I care about y alone, I'm going to fix a value y, and then I'm going to sum over all possible x values of my probability distribution with that y value fixed. Let's take a look at an example. So we have two pens being selected from a box that contains 3 blue pens, 2 red pens, and 3 green pens. And the pens are being selected randomly. So we're going to have x is the number of blue pens selected, and y is the number of red pens selected. So let's first take a look at what our limiting factors are going to be on our random variables. So x is the number of blue pens selected, So X is interested in blue pens, and there are 3 blue pens in the box. Now, Y is interested in red pens, so Y is going to be capped by the number of red pens in the box. And finally, the other limiting factor to our random variables is going to be how many. Then finally, the last limiting factor on our random variables is going to be the number of pens we're actually selecting. So we're actually selecting 2 pens, so we'll never have more than 2 pens of a color. So when we're setting out to find the joint probability function f of xy for a pair of discrete random variables, the first thing we need to do is come up with the possible points xy, the values that all of our random variables can take and how they can be paired together. So xy can be, there are 3 green pens in the box, so the 2 pens I select could both be green. And if that's the case, then I will pick 0 blue pens and 0 red pens. Now there are enough blue pens in the box that I could select both pens as blue pens, and there are also enough red pens in the box that I could select both pens as red pens. So my values for my random variables are going to be anything from 0 to 2. But the total between the two, if I add x and y together, I need to have no more than 2 pens. And the green pens can always make up the extra, and so I can have less than 2 pens. So I can have 0, 0. I could have 1 blue pen and no red pens. I could have 2 blue pens and no red pens. I could have 1 blue pen and 1 red pen. I could have no blue pens and 1 red pen. I could have no blue pens and 2 red pens. And those are my 6 possible points. Now, for each of these points, I need to find the probability that I select pens in that way. So the first thing that I need to find out is how many ways can I select 2 pens if I don't care about what color they are. So there are 8 possible pens there. So there are 8 pens to choose from, and I'm going to choose 2 of them. If I do 8 choose 2, then I come up with 28 possible ways to choose pens. This is going to serve as the denominator for my probabilities. Now I need to know how many ways can I select 0 blue pens and 0 red pens. This is going to give me my f of 0, 0 value. Now choosing 0 blue pens and 0 red pens corresponds to choosing 2 green pens. Since there are 3 green pens to choose from, and I'm choosing 2 of them, then I have 3 choose 2 ways to choose 2 green pens, or 3 possible ways to choose 2 green pens. So this is going to serve as my numerator in my probability. So my joint probability function evaluated at 0, 0 is going to be 3 over 28. Similarly, if I want to know what my joint probability function is for my point 1, 0, where I have 1 blue pen and 0 red pens, I need to know how many ways can I select 1 blue pen and 0 red pens. Now, the ways that I can select 1 blue pen, since I had 3 blue pens to choose from, I'm going to be able to take 3 choose 1, and that gives me my 1 blue pen. Now, to get 0 red pens means that my second pen must be green. So I can take the 3 green pens and choose one of those as my second pen. And then, because of my counting multiplication rule, I'm going to multiply these 2 numbers together to get the total number of ways. So 3 choose 1 is 3, and 3 choose 1 is 3, so I get a total of 9 possible ways to do this. Now 9 is going to be the numerator for the value of my joint probability function evaluated at the point 1, 0. So that probability will be 9/28. And I can continue in the same manner to get the value of my joint probability function at the 4 other possible points. Now, just like before, when I had a discrete probability distribution, I could make a table of values that the function took on. And I can do that again for my joint probability distribution when I'm dealing with discrete random variables. The difference is here I need both an x component and a y component. So the x component will be represented by the columns, and the y component will be represented by the rows. So I would put my 3/28 that I found for the point 0, 0 in at the x is 0 and y is 0 entry point. So this one will be 3/28. And I can put the value that I found of 9/28 in when x is 1 and y is 0. So I'll have a 9/28 here. And I can fill in the rest of the values. Now notice the entries, whenever I would have chosen more than 2 pens, are 0, because there's no possible way that I do that. And I can add across my row to get a row total. So here I'll have 15/28, 12/28, and 1/28. And this makes it easy to add up so that I can see that I have a total probability of 1. And I can do the same thing with columns, double check myself. So I have 10/28, I have 15/28, and I have 3/28, and I add those across, and I also get a total probability of 1. So there I have my joint probability density function for my discrete random variables x and y. Now, in part B, I'm asked to find the probability that x and y fall within this region that's determined by x plus y is less than or equal to 1. I often find it helpful to look at these equations that define the region and think about what that means in terms of the context of my problem. So x plus y is less than or equal to 1 means I have blue pens and red pens added together, the number of them that I have, and I have no more than 1. So no more than 1 total red and blue pen combined. So then I can look in my probability density function and see what satisfies this. So in my probability density function, if I have x is 2, then I'm going to have 2 blue pens, which does not satisfy the bound that I have for my random variables. So I need x to be at most 1. So I'm going to kind of put a line there to remind myself. Similarly, when y is 2, I have 2 red pens, and that is also not okay for having no more than 1 total red and blue pens. So I'm going to put a line there to remind myself that y should not be 2. So then I look at the other possible points. If I have y is 1 and x is 0, I have 1 red pen and 0 blue pens, which satisfies my no more than 1. So this is an okay value to be in. Now, if I look and I have 1 and 1, so 1 red pen and 1 blue pen, then I have 2 total red and blue pens combined, which is not okay. So this value is not going to be allowed in. And I can kind of wall it off. And when I do that, I've kind of made a region here. Let's look at what else falls inside of this region that I've made. So x is 1 and y is 0. I have 1 blue pen and 0 red pens. That is no more than 1 total combined, so that's okay to be in here. And then 0 and 0, 0 blue pens, 0 red pens, gives me no more than 1 of them combined. So those 3 values are okay. So now to find the probability that we're asked for, so the probability of xy being in the region A, where our region is xy points given that x plus y is less than or equal to 1 is going to equal, and it equals the sum over a. So it was written like this in our definition. And what this means is we're taking all of the points in our region A and we're summing over them, the values of the function. So this is going to equal f of 0, 0 plus f of 1, 0 plus f of 0, 1, which is going to equal 3/28 plus 9/28 plus 6/28. And I add these together, I get 18/28. And I could simplify that down to be 9/14. And that is the probability that I have no more than one total red and blue pen combined. Now, if I think about marginal distributions in relation to this example, marginal distributions fix the value of one of my random variables while letting the other random variable take on different values. So, in this example, I could fix the number of blue pens I have at 0 and let the number of red pens be any possible value that goes with 0. So I could have the points 0, 0, because 0 red pens. I could have 1 red pen, so 0, 1, and I could have 2 red pens, or 0, 2. Now the marginal distribution wants to know, basically, the probability of having 0 blue pens, and what I do to find that is I'm going to add up all of those possible values, which actually ends up being the column total for my joint probability distribution at the fixed value x that I was concerned with. Now, if I instead fixed x at 1, I would be adding up down the column corresponding to 1, or if I fixed it at 2, I'd be adding up down the column corresponding to 2. So this right here is actually my marginal distribution, g of 0, where I fixed x at 0. And it's going to be that 10/28 value, where I've added up everything in the column. Now if I instead fix a y value at a single point, so say I'm concerned with having 0 red pens, then I again let the number of blue pens vary while keeping the number of red pens fixed. So I could have 0 red pens and 0 blue pens, 0 red pens and 1 blue pen, 0 red pens and 2 blue pens, and what that ends up corresponding to then is my row total across where I had my y value for my number of red pens fixed at 0. So this is actually going to be my marginal distribution h of 0, where my y value was fixed at 0, which will give me 15/28, which was that row total. Now, if you've only had single variable calculus so far and only dealt with a single integral at a time, then I encourage you to pause this video and take a look at the one about taking double integrals and multiple integrals. That'll help you out as we move into continuous joint probability distributions. Now, if our random variables are continuous instead of discrete, we're going to have some similarities and some differences. So when we're taking a look at our joint density function f of x, we're still going to need the values that that function takes on to be greater than or equal to 0 for all possible values that our random variables x and y can take on. And since x and y are continuous random variables, much like we did when we were finding the probability density function with a single continuous random variable, we're going to be taking integrals rather than sums. Since we have two variables, we need to integrate over both x and y, and when we do that, we should get a value of 1. Now, if I want to find the probability that the random variables fall in a region A, I'm actually going to integrate over the region, and since the region has both an x and y dimension to it, I'm going to be integrating with respect to x and y over the region, and this is the case for any region in my xy plane. And just like we could in the discrete case, when we're dealing with a joint probability distribution, we can look at the marginal distributions for x alone and of y alone. So g of x being the integral over my joint density function with respect to y is going to be the marginal distribution of x alone, and h of y being the integral over my joint density function with respect to x is going to be my marginal distribution of y alone. Let's take a look at an example. So we're going to have a business that operates both a drive-in facility and a walk-in facility. On a randomly selected day, we're going to have x and y be random variables that represent the proportions of time that the drive-in and the walk-in facilities are in use. X will be drive-in, y will be walk-in. And we're going to suppose that we have this density function for our random variables that's given. So the first thing that we want to do is we want to verify condition 2 of the definition. Now, condition 2 of the definition said the integral from negative infinity to infinity, the integral from negative infinity to infinity, f of xy dx dy equals 1. So we're looking to verify this. F of xy is going to be 0 everywhere outside of the window that's given, and the integral of 0 is 0, so we don't need to worry about that part. So to verify this, we really need to look at the window given. Now remember, when we have a double integral, it's like there's parentheses around the inner integral. So I have a dy outside and a dx inside. So my bounds for integration, my outer integral is going to go with my y values. So y is going to go from 0 to 1. And my inner integral is going to go with x values, and my x window is also from 0 to 1. Now this is the only time when my function is not 0, so the integral is not 0. And I'm going to be using that piece of the piecewise function that was not 0, so the 2/5 times 2x plus 3y part. So to evaluate this, the first thing that I would do personally is I would say there's a constant there, and I can pull constants all the way out front. So I can actually move that 2/5 out in front of an integral and then out in front of an integral again. So all of this is 2/5 times the integral from 0 to 1. And then I've got my parentheses with my integral 0 to 1 of 2x plus 3y dx, and my parentheses, and then dy. Following order of operations, I need to do everything inside of my parentheses first. So I'm going to leave everything outside alone. So I've got 2/5, the integral from 0 to 1, something happening in my parentheses, and then a dy. Now, inside my parentheses, I need to integrate with respect to x. That means that x is the only thing being treated as a variable. So I'm going to integrate 2x, that part of that sum, with respect to x. X is a variable, so it gets treated as such. So I have 2 times x, and I'm going to add 1 to the exponent. The exponent was an invisible 1, so now it's going to be a 2. And then I divide by that new exponent. And then the 3y, now remember, y is not a variable in this case. So 3y is like a constant. And when we integrate a constant, we leave it the same and put a variable with it. So I'm actually going to now evaluate this from my x values 0 to 1. So again, I'm still not done the stuff in the parentheses, so I'm going to leave everything outside of the parentheses the same. And then I'm going to evaluate what's inside. Inside, I'm going to plug in 1 for x. So I'll have 2 times 1 squared over 2 plus 3y times 1. And I'm going to subtract from that, plugging 0 in for x. So I'll be subtracting 2 times 0 squared over 2 plus 3y times 0. Now I still have to simplify the stuff in my parentheses, so I'll leave everything outside of my parentheses the same. And inside my parentheses, I'll now have 2 times 1 squared is 2, divided by 2 is 1, plus 3 times y times 1 is going to be 3y. And then 2 times 0 squared is 0, divided by 2 is 0. 3 times y times 0 is 0, so all of that goes away. So I don't have to subtract out anything. So now I've taken care of the stuff in the parentheses, and I have an integral from 0 to 1 of 1 plus 3y dy. I'm going to integrate that with respect to y. So when I do that, I have a constant 1, which when we integrate a constant, we multiply it times the variable. And then I have the variable y paired up with a 3, so I have 3y. So I'll have 3y, adding 1 to my exponent makes it squared, and dividing by that new exponent of 2, I'll have 3y squared over 2. I'm going to be evaluating that from 0 to 1. Now, I'll still have my 2/5 outside of my parentheses because I have more to deal with inside of my parentheses. So 1 times y, I'm going to plug in 1 for all of my y's, so I'll have 1 times 1 plus 3 times 1 squared over 2. And I'm going to subtract from that, plugging 0 in for y, so I'll have 1 times 0 plus 3 times 0 squared divided by 2. So when I simplify this, I'll still have my 2/5 hanging out front. I have 1 times 1, or 1, plus 3 times 1 squared is 3 divided by 2. So I have 3 halves there. And then everything inside of my parentheses here zeroes out, so I'm subtracting nothing. And then I'm left with just some simple arithmetic to simplify this. So 1 plus 3 halves is really 5 halves. 2/5 times 5 halves is going to be 1. And that actually did exactly what I needed to do. I needed to verify that second part of the definition. Now remember, part B was asking me to find the probability that my random variables fall in this region A, and I'm given bounds for x and bounds for y for my region. Now in the definition, it told me that this is equivalent to the double integral over that region A. For part B, I'll be taking an integral. I'll have my f of xy inside, and I'm integrating over A with respect to x and respect to y. Now, again, I'm going to be looking at this. Remember, there's like these parentheses that aren't written there. So my outer integral gets paired up with y, and my inner one gets paired up with x. So I'm going to put my bounds of integration in that way. So I'm looking at the bounds of the region they gave me, and y is going from 1/4 to 1/2. So those will be my bounds with respect to y. And then in those parentheses that I'll actually write now, I'm going to be integrating with respect to x. So I'll be putting the x bounds of my region, which is going from 0 to 1/2 from what was given. And notice f of xy, these bounds fall completely within the bounds given for just the first piece of my joint density function. So I'll be using 2/5 times 2x plus 3y as my function. So again, my constant can come out front of all of the integrals, so I'll have a 2/5 times the integral from 1/4 to 1/2, and I'm going to start taking care of the stuff in the parentheses. So I'll have a parentheses integral from 0 to 1/2 of 2x plus 3y dx, and a dy outside of the parentheses. So I'm actually going to integrate that inside of the parentheses, leaving everything outside of the parentheses the same. And I'll end up with 2x squared over 2 plus 3yx, evaluated from 0 to 1/2. And then I'm going to do that evaluation inside of my parentheses. So I have 2/5, the integral from 1/4 to the 1/2, and my dy hanging out outside of my parentheses, and plugging in 1/2. My 2's cancel each other out, so I really have 1/2 squared plus 3y times 1/2. And plugging 0 in for x zeros both of those out, so I won't be subtracting anything. Now, you get to simplify what's in my parentheses a little bit more, leaving everything outside the parentheses the same. So 1/2 squared is really 1/4, and 3y times 1/2 is 3/2 y. And at this point, I don't actually need my parentheses. So now I can do my integral with respect to y. My 2/5 stays the same, and I'm going to be integrating this. So I'll have 1/4 y, because y is my variable now, and plus 3/2 times y squared over 2. And this is going to be evaluated from 1/4 to 1/2. So I'm going to do a little bit of simplifying, and then I'll do my evaluation. So I have 1/4 y plus 3/2 times y squared over 2 is going to be 3/4 y squared. And I'm evaluating this from 1/4 to 1/2. Now doing the evaluation inside the parentheses, I'll have 2/5 staying the same outside. And then I'll have 1/4 times 1/2 plus 3/4 times 1/2 squared minus, plugging in 1/4, I'll have 1/4 times 1/4 plus 3/4 times 1/4 squared. Now I just have to simplify everything, so I still have 2/5 out front, and I'll have 1/4 times 1/2 is 1/8, plus 1/2 squared is 1/4, and 3/4 times 1/4 is 3/16. And I'm going to subtract from that. 1/4 times 1/4 is 1/16, plus 1/4 squared is 1/16, times 3/4 is 3/64. So continuing my simplification, 2/5 stays out front. I can get a common denominator with all of this. 64 would be that. So I would have 8/64 plus 12/64. I can distribute my negative, so I end up with minus 4/64 minus 3/64. And continuing that simplification just a little bit more, my 2/5 stays the same. And now I can add and subtract all of my numerators. So I have 8 plus 12 is 20, minus 4 is 16, minus 3 is 13 over 64. And then I just have this multiplication to do. And I noticed that the 2 can cancel into the 64. So this becomes 32, this becomes 1. So I have 1 times 13, or just 13 in my numerator. And in my denominator, I have 5 times 32, or 160. So the probability that my random variables fall within the regions given is 13 out of 160. And to find the marginal distributions in the continuous case, you really are just taking the integral over one of the variables and coming up with a function in terms of the other variable that you didn't integrate over. Now we also can talk about a thing called the conditional distribution. And the reason that this is coming up when we have more than one random variable is because we're basically saying one of these random variables turned out to be this. Now what could happen with the other random variable? So we're asking what the probability of y is given that x already had this outcome. So we write this conditional distribution as the function f, that is our joint probability distribution, of our random variable y value, given that our random variable x value already happened, using that bar for given like we have before. And this is going to equal the joint probability distribution for our xy point divided by the marginal distribution of x. Similarly, if instead I fix y and say y became this given value, so what's the probability of a certain x value occurring now? I take my joint probability distribution and I'm going to divide it by the marginal distribution of y. And conditional distributions work the same whether or not the random variables that we're working with are discrete or continuous. So you only have to remember this one idea for conditional distributions. Another time when it doesn't matter whether the random variables we're working with are discrete or continuous is when we're trying to determine if the random variables are in fact statistically independent. So if we have two random variables x and y, and we have their joint probability distribution f of xy, and the marginal distributions g of x and h of y, then we say that they're statistically independent if and only if the value of the joint probability distribution at xy is equal to the product of the marginal distribution of x and the marginal distribution of y for all possible xy values within the range of our two random variables. Also, we can expand this out. This is true when we have more than two random variables. So I could have x, y, and z, say, and this would be the case if the joint probability distribution of the three variables agreed with the product of the marginal distributions for each one of those variables one at a time, multiplied together, or all of the possible pairings of values for the random variables.